Okay, this is Energy and its Conservation, Chapter 11. So in Chapter 10, we learned about different types of energy and machines and how that energy can be translated. As long as energy is conserved, you can change your work, your force in and your force out, your distance in and distance out. So today we're going to look at different forms of energy. We talked about work and power and energy in the last chapter. Talk about forms of energy. So that means we're going to talk about gravitational potential energy, kinetic energy, and we're going to relate work to energy, which is pretty easy because work is different. So energy is the ability to do work. It can be stored and transferred. There are lots of different types of energy. In mechanics, we deal with gravitational potential energy, kinetic energy. We even deal with heat energies, technically mechanical energy. We won't really talk about chemical energy. We also have electrical energy. We have elastic potential energy. There's some different types of energy. So the first type we're going to learn about is kinetic energy, and that is any time it is moving. So kinetic energy, K, or KE, is equal to 1/2 mv squared. This was in the last chapter. I showed it to you. I just wanted to make sure you had it before. Now we're actually going to use it a lot. Kinetic energy is a type of energy, so it is measured in joules, just like work is. So anytime your object has some sort of velocity, it is going to have kinetic energy. We have the work kinetic energy theorem, which again I showed you in the last chapter. Just want you to know that we're still going to use it, and we'll probably use it a lot in this chapter.
Please check your list of students scheduled to take the writing practice test today. Anyone that has Miss Smith for English, you have a list.
Anybody have Miss Smith for English? The list is not by first period teacher. It is alphabetical. There's about 100 or so people on the list. Very difficult to look through. Okay, good. We're good with that one. All right. Let's look at rotational kinetic energy. Anytime your object is rotating, you're going to have rotational kinetic energy. Now the I can be translated into some sort of mr squared or 1/2 mr squared, depending on what it is that's rotating. right? Remember those I, that capital I, is the moment of inertia. It's whatever it is. So for this one, if it's rotating around the center, it's 1/12 mr squared. It's rotating about the end, it's 1/3 mr squared. That's what the I would be. So when you're doing the rotating stuff, you need to tell me what kind of object it is and look up its moment of inertia. And then you can translate the omega into velocity by doing the translational velocity, which is v equals r omega. So v over r equals omega. So if you needed to get this into some sort of velocity instead of angular velocity, you can translate it using this. Now you won't have to deal with anything rolling down a hill. My AP students do. But you guys don't, so you probably won't encounter anything where you actually have to translate stuff. But it is possible, and someday you might take physics in college and have to do that. Okay, I see one red cup. All right, the next one we'll talk about is gravitational potential energy. Anytime an object has height, it is going to have gravitational potential energy. So I'm going to take my duck, and if I put it up here, it has the potential to fall. So it can take that potential energy, gravitational potential energy, and turn it into kinetic by moving. Now, each of these things is a different type of energy, so they're all measured in joules. Each one of these is joules. It's just energy. Okay, elastic potential energies. This is anytime you have something, pretty much you go talk about springs. But sometimes it can refer to like rubber bands. Not usually, but sometimes they'll be like, okay, a rubber band has elastic potential energy using this equation. So it is possible. So if it is a spring or a rubber band, mostly just a spring though, you can use this one, potential energy, and we'll call it SP for spring, 1/2 kx squared, where k is that spring constant, and x is the distance from the equilibrium. And if you guys don't really remember anything about springs, we did cover it when we talked about Hooke's law and forces. Here is your spring. Where it hangs, that's its equilibrium point. So x is the distance away from that. So if I push it up, now it has some sort of distance, and that would be its x. Or equilibrium, if I stretch it down, the distance that I stretch it down is x. It was back in chapter 6 or something like that. It's a long time ago. Don't worry. It's a spring, use potential energy. Elastic potential. And the rubber band itself is going to have some sort of K. And, if you just leave a rubber band just sitting there, or if you pretty much pop before you stretch it, that would be its equilibrium point, and then you stretch it. Again, they don't use rubber bands very much because I'm pretty sure normally they have a different equation, but there are a couple of problems where it's like, well, it acts like a spring here. So. All right, and then I have one more famous equation for you, if you're ready. And that is E equals mc squared. This is called rest energy. So it's the energy stored by the mass itself. I won't really be asking you to calculate this too much. I think there's a couple of problems in there where it's like how much rest energy does it have. But we're not going to put it into our big main mechanical equations for the most part, because we're not talking about nuclear explosions or releasing any of that rest energy. The rest energy here will be the rest energy here, because we're not breaking apart atoms or anything like that. So I want you to have it. They'll ask you like one question, but it's the energy due to the fact that it has mass. We call that rest energy. It is a potential energy, if you wanted to be more specific. Potential energy, but they call it E equals mc squared, because if we did PE equals mc squared, no, we didn't know what we were talking about. We will talk more about this rest energy when we get into nuclear physics at the very end of the year, in case you're interested in it. But it's more complicated because you start talking about a little bit more chemistry type stuff, because we're talking on the atomic level. So we're just trying to talk about mechanics of energy. I should say here, c is the speed of light, 3 times 10 to the 8, in case you're interested. Again, we'll talk more about that at the end of the year when we do this stuff. You need to know that number. It's 3 times 10 to the 8. It's also on the inside cover of your book, I think, like the back cover. I think c is in there. Okay, so now how do we figure out all these energies? I've told you if it's moving, rotating, has height, is a spring, or a mass. Those are the different types of energy. But because energy is constantly changing from one form to the other based on what it's doing, we need to kind of be able to pinpoint those energies. So right now, what kind of energy does this book have? Be more specific. Is it potential spring, gravitational, mass? Yeah, this one has rest energy. Now, for your problems, we're pretty much going to ignore the fact that it has rest energy, because the rest energy here is going to be the same as here because the mass didn't change. So does it have any energy other than rest energy? Okay, so it doesn't. So what I'm going to do is I'm going to do work on this book. I'm going to take my Cinnamon Life cereal that's stored up in my body, and I'm going to put it into this book by lifting it up. What type of energy does it have now? Potential gravitational energy. You got to be specific. It can't just be potential. What kind of potential? Okay, if I drop it, what kind of energy does it have when it hits the table? It's dropping right before it hits the table. Kinetic, because it's moving. So that potential, well, my life cereal chemical was turned into potential gravitational, which was then turned into kinetic and used up. Okay. What else can we do? How much energy did it have when it was right here, on its way down? What types of energy did it have? Kinetic and gravitational potential energy. So it had 2 different types. Now let's talk about a very complicated thing, which I won't ask you to do as a problem, but we're just going to pinpoint its energies. You have an inclined plane, and you have an object that is rolling down the inclined plane. It rolls down at the bottom. So it's still rolling. Before it starts to move, what kind of energy does it have here? Potential gravitational, because it has height. At this point, when it's rolling, when it's moving, what kind of energies does it have? Okay, it has kinetic energy, and it has kinetic energy rotational, because it's rolling down and it's spinning as it's rolling. So it's not only is it moving, but it's also spinning. So it has to have both. All right, now, when it's at this point, what kind of energies does it have?
All three.
All three. Gravitational potential energy, kinetic energy, and rotational kinetic energy. Now, if we assume that there is no friction, or friction isn't really taking any work out of it, this would be a conserved system. So if the system's conserved, that means the energy initial is going to equal the energy final. So the energy here has to equal the energy here, has to equal the energy here. Because no more energy was put into this. We didn't spin it. We didn't push it on its way down. We just set it here, so it had all gravitational potential energy, and then some of that gravitational potential energy went into spinning it and moving it down. And then all that potential energy that was left spun it more and moved it down more. So it'll get faster and faster as the potential turns into kinetic. So this is true for any conserved system. The energy at one point will equal the energy in another. All right, so here's a practice. A 2-kilogram ball. Let me erase this. All right, a 2-kilogram ball is held at a height of 3.5 meters. It is then dropped. Part A, what is its initial potential energy? Okay, so what's the 2 kilograms? Mass. What's the 3.5 meters? Okay. What are we looking for in part A? Gravitational potential energy. So here's the ball. It's going to fall down here. This is 3.5, and it starts here. How much velocity does it have in the beginning? 0, because it's dropped. So it's not moving at the beginning. So what type of energy does it have here? Potential. What type of energy does it have here?
It stops there.
Right before it hits the ground.
Kinetic energy.
Kinetic energy. Yeah, all of your problems will ever only be right before it hits the ground. We won't talk about impacts anymore, ever. Okay, and how much energy does it have right in the middle here?
Some kinetic.
Good. Some potential and some kinetic. Is there anything taking energy out of the system? Any air resistance or friction or anything? No. It's a conserved system. So that means that the energy here is going to equal the energy here, which is going to equal the energy here. So if we know this, we can find this. If we know this, we can find these probably. We know what height we're looking at. Okay, so part A, we're looking for potential energy gravitational, the equation, mg. Plug in our stuff. We get 2 times 9.8 times 3.5. Notice that it's not negative 9.8 because we're talking about energy. Energy is not a vector, it's scalar. We don't say that we have 4 joules to the right. We just say we have 4 joules. 68.6. Yeah. So since we found the energy at A, we know that these two things have got to equal 68.6, and the kinetic energy at the bottom needs to be 68.6. Which actually, no, that's right. Okay, so this is at A, potential energy at A, initial. Okay, part B, what are we looking for?
Kinetic energy.
Kinetic energy where?
At the end. Oh, the initial is 0.
This is initial, so it's at A. And how fast is it going at A? 0, so it's not going to have any kinetic energy. Because it doesn't even have it, right? A, B, and C. That should be C. Okay, part C. What's the ball's final potential energy? Oh, this should be C, sorry. What was it? 0, because it's at the ground. which would be 0 joules. All right, D, what are we looking for in D? Final kinetic energy. Let's see. 68.6, perfect. Because we didn't lose any energy. We didn't gain any energy, so the total energy has to be the same. It just converted from potential to kinetic. Now comes a little bit tricky. It's actually not that tricky, but what is the ball's final velocity right before it hits the ground? How do I figure this out?
What do you take the moment?
Nope, that's for rotational only.
Oh.
Everybody know what to do?
Distance over time.
Nope. Look at your equation for kinetic energy. Yep. So kinetic energy equals 1/2 mv squared. What's the kinetic energy?
68.6.
Good, 68.6. Equals 1/2 times our mass, which is 2, gives us our v squared. So these actually cancel. And it's just going to be the square root of 68.6. Is it 8.2?
8.3, yeah.
8.3. There you go. Yes.
I don't understand, like, D.
Part D?
Yeah, I don't understand. Why is it the same?
Okay. It started with 68.6 joules, right? Was there any energy added to the system as it fell? Did we push on it? Does it have a motor? Okay, is there any air resistance that it told us? Is there any air resistance? Is there anything slowing it down, pushing against it, taking energy out of it? Does it have wings? No air resistance. So there's no way that energy could be transferred in or out of the system. If it starts with 68.6 joules, it has to end with 68.6 joules. Yeah, because the energy was conserved here. If there was some sort of friction or some sort of work done on it, that means that we'll be taking energy out of the system or adding it into, and then they wouldn't be equal. But for most of your problems, they'll be conserved. If they are not conserved, then you can use this equation, where work is equal to, and it doesn't have to be the change in kinetic energy, it could be the change in any energy. So for instance, if I was doing work on the book to lift it up, I could do the work that I did, force times, its weight, times the distance I lifted up. And then since it's moving up, and it could still be 0 degrees, that's fine. Is going to be the change in energy. In that case, I was changing potential energy, so it could just be changing. And then I could set that equal to this and find its height. How do you guys feel about this? There's a lot of little equations, but you're looking at the conserved energy over here. It should all be the same. Unless it says otherwise, which it should. So let's start our clicker questions. Here's our first clicker question.